Hello, thanks for checking out this video where I'm going to talk about PID controllers. So this year at the university I've been teaching a new course, and part of that course involves using a PID controller to control the speed and the position of a robot. And what I can tell you is students really struggle on the basics of what a PID controller is and how to actually implement it in hardware. So that's the purpose of this video. I'm not going to give you a deep theoretical or mathematical analysis on what a PID is. I'm going to give you a very practical overview and explain exactly and show you how to implement it on a microcontroller. So let's make a start. Okay, so what is a PID? So it stands for proportional, integral and differential control, but that's a bit of a mouthful. Basically, it's a control methodology that uses feedback to adjust the amount of actuation or drive to a system. So let's look at these examples on the screen. We've got temperature, speed, intensity and position. So here we need a sensor, so it could be a thermocouple for the temperature, or it could be a light dependent resistor for the intensity, or a radar for the position. So you have a sensor. Let's just take that Tesla example. Let's say we want to maintain a fixed position of 10 feet away from the car in front. So 10 is what we're trying to get, and our sensor's measuring that constantly. Every second it's measuring that distance. And we need our controller to say, wow, we're too close, slow down, or wow, we're not close enough, speed up. So it's a controller that acts based on feedback to reduce error. Now, don't turn off. I can see you going to the mouse button there to click off this video because this diagram's everywhere and you don't like this diagram. I completely agree with you there. This diagram's really great if you already understand what a PID does. It doesn't really help you in understanding how the PID works or what it does. So let's ignore that diagram and let's go and look at some practical examples. The basic components of a PID, or a control system that implements a PID, is what you see on this slide. So conceptually, we need a controller, some kind of process. That could be a heater, it could be a light bulb, it could be a Tesla car, it could be anything. And we need a sensor that's measuring the output from that process. So if it was a heater, you'd be measuring the temperature. That's fed back into the controller that then adjusts its output to affect the process. So let's look at a practical example of that. Almost every house has got a system like this. In your house, or certainly in my house, I have a boiler, so that applies gas actually to heat the water to a certain temperature. That water's pumped through the radiators in the house to control the temperature in the room. Controlling all this is our control system. It looks something like this in my house. Basically, I enter a value of the temperature I want in the room. So for example, 22.5 degrees, that's my set point. In here, there's a thermocouple or something measuring the temperature, and basically it measures that value and it says, oh, hang on, that's below our set point. Increase the power to our boiler or increase the amount of gas we're burning. That increases the water temperature. That increases the temperature of the radiator. In turn, the room warms up. We measure that value again and we go through this loop indefinitely to try and maintain that set point temperature. That is a practical control system. But what does good look like? That's important. So it's all right saying we want to control something, but what do we actually want that response to look like? So taking our practical example, now I've set my set point to 25 degrees C. When I've woke up in the morning, my heaters are all off. So my house is at a chilly 10 degrees. What I want is when I switch my switch on my heating system, I want the temperature in my room to rise up as quickly as possible to that set point temperature. That is what we'd call a critically damped system. It doesn't overshoot and it doesn't take forever to reach the set point temperature. It does it as quickly as possible without any overshoot. If things don't go right, if we don't have a very well controlled or optimized control system, we might get a response that looks like this. So when I turn that heater on in the morning, the temperature shoots up, but it shoots right up to 32 degrees or something like that. My room's super hot, I'm burning loads of gas. And eventually over time it settles to that set point value. This is an underdamped response. This is not great. We're trying to avoid this in some scenarios. Imagine this was that Tesla example with position. This might be the back of the car you're trying to not hit. So you get the idea. You want a very nice, steady response to reach the set point. And the flip side of this, the alternative, is the overdamped response, where your heater's, you're just providing a tiny little bit of gas, slightly warming the water up, and it's slowly heading towards your set point. It might never even reach it. That's an overdamped response. There's no oscillations, but it doesn't reach the set point. I've made a little system to demonstrate this. So it's a heater, but it's not the heater in my house, obviously, because that's a bit slow. So what I've got here, I've actually bought a 12-volt heating mat. It's basically just a big resistor on a sticky pad. So you apply 12 volts between those two wires and it warms up. It reaches about 50, 60 degrees. I've got a Raspberry Pi PICO microcontroller, so I'm going to be working in MicroPython today for my examples. I've got this thermocouple amplifier, I think they call it. Basically, you connect a thermocouple to it and it provides you a digital measure of the temperature. So that's my sensor in this example. And I'm going to use a switch, a MOSFET switch, to control the heating power. So what I'm going to use is pulse width modulation here. So if I want my heater off, I'm going to keep the gate of that MOSFET at 0 volts. If I want the heater on 100% of the time, I'm going to keep the gate of my MOSFET at 3.3 volts. If I want my heater at 50% power, what I'm going to do is I'm going to have my MOSFET off 50% of the time and on 50% of the time. So this is pulse width modulation, and I'm changing the duty cycle, so the ratio between off time and on time. That's how I'm going to adjust the power applied to the heater in this example. Let's go and have a look at me building that circuit, and I'll talk through a bit more what I'm doing. Here I begin by plugging the components into the board. So the Raspberry Pi sits in the middle with the gap between the pins, obviously, to stop them shorting out. I put the MOSFET in and I put the MAX 6675 in. So the heater goes between the MOSFET drain, which is the middle pin, and the DC power supply. The gate to the MOSFET goes to the Pi Pico, so it's the Pi Pico that determines whether the gate's high or low, and that's connecting to pin 19 on the Pi Pico, which is actually GPIO 14 or GP14 in Pi Pico terminology. I connect the thermocouple amplifier as well to just several of the GP lines and set them up correctly in the code, and that's really it. It's quite a simple circuit. There's not really much to think about here. Just got to make sure that you don't put too many volts into your Pi Pico. And also, critically about the MOSFET switch, must be a logic level FET. So if you just go and buy a random MOSFET from some supplier, chances are its threshold voltage is around 3 or 4 volts, which means the Pi Pico can't turn it fully on. Whereas if you get what's called a logic level FET, it'll switch fully on at 3.3 volts provided by the Pi Pico. So it's quite important you get one of those, or you might find your MOSFET's getting really hot and not properly switching. But other than that, it's a really simple circuit. You can follow it from earlier in the video. If you wire it up as shown, it'll work as expected. Okay, so let's have a look at the proportional parts of the PID. So no matter what system you're trying to build or trying to understand, my recommendation would always be to build just the P, the proportional part of the controller first, and see what happens. It's the simplest to do, it's the simplest to understand, and it's the simplest to tune. So focus on the proportional control to begin with, and it's super easy. So what we're going to do is we're going to get our microcontroller to measure the current temperature and compare it to the set point, and that's going to generate an error. So here, in this example, the set point's 25. Current temperature in my house is 8 degrees. The error is 17 degrees. At a different time, so a little bit later, here my set point's still 25 and my error is now 7C because the temperature in the room's warmed up, it's got closer to the set point. So the error, the difference between the two, is lower. That is the first step, calculate the error. The next step is to calculate this proportional term. The proportional term is basically what we're going to provide to our MOSFET to tell it how long to turn on. Do we want to provide a value of 100 to make it stay on 100% of the time, so really apply a lot of heating power, or do we want to provide a term of 0 to keep it switched off because we've actually exceeded our set point? So in this little example, I've guessed a value of Kp. So Kp is a constant. I'll explain a little bit more when I talk about the practical example and I show you on the circuit. But let's just assume that is a constant value of 5. And just as I said, if we get a value of 100, the boiler's on at full power. If we get a value of 50, we're at half power. So let's have a look now at this time point 5 here. This time here, we've got a big error. 17 degrees is a big difference in temperature. So to calculate our sort of control parameter, what I'm going to do is take that error and times it by this constant value. So 17 times 5 is 85. This means the boiler's on at 85% power. It's on quite a lot. So a big error means lots of heating. That causes the temperature to rise. And now let's have a look at time 20 minutes. So now the error is only 7 degrees C. It's smaller. 7 times 5 is equal to 35. So that means our boiler's on at 35% power, nowhere near as much heating. And that's going to cause the temperature to not rise as quickly. So that is the essence of proportional control. The amount of drive signal you give to your heater is proportional to the amount of error you've got. So the smaller the error, the smaller the heating. And in an ideal world, when you've got no error, you've got no heating and you're perfectly at your set point value. And if you drop below that set point value, you get some heating and that increases the temperature. So you should maintain that value indefinitely. Let's have a look practically how that looks and how we code it. So I'm here in Phony. I've connected my Pi PICO. It's connected to COM9 on my computer, as you can see. And if you look, I've actually got my Pi PICO W now. So that's slightly different to what you saw me wiring up a moment ago. A word of advice, don't connect your 12 volt DC power supply to the input of your Pi. It destroys it. So I've had to quickly swap that out because I basically messed up and connected my 12 volt inputs basically onto that white wire which goes to the Pi. Destroyed it. Not to worry. Anyway, so as you can see, I've got my thermocouple just taped onto my heating pad just here. And the output of this Pi, this GPO14 I think it is, basically goes to the gate of the MOSFET, and if that's at 0 volts the heater's off, if it's at 3.3 volts the heater's on full, and if it's got like a 50% duty cycle, so it's on half the time, then you're going to get half the heating power. So it's as simple as that. Let's go and set this up now in Phony to actually read the thermocouple and turn the heater on and off. To do that, we need to import a few libraries. So the first one is for the thermocouple. So that's the thermocouple in. Now we need some GPIO control and some PWM control. So those are the libraries I need, basically the thermocouple controller and the pin GPIO controller and the PWM controller, and finally time so we can implement sleeps and things like that. So let's just look at that code. We basically define the pins of the sensor. We've created a sensor object. Here we're going to do a sensor read. We're going to print that sensor temperature, and then we're going to do a sleep for a second, and this repeats forever. So let's run that. We should just see the temperature in the room plotted and text on the screen. And as you can see, there's the temperature in my room. And what I really like about Phony is you can go to view the plotter and it actually makes you a graph of that. So that's just the temperature in the room. Let's set up the PWM now and make a simple control loop. So to do that, I need to create a PWM object. I need to set the right pin. So I'm using GPO 14 on the Pi PICO, which is annoyingly pin 19, but anyway, not to worry. For the frequency, this actually doesn't matter that much. So really, if you switch too fast, you incur a lot of switching losses in your switch, and that wastes heat, or wastes energy, should I say. And if you switch too low, then that starts influencing how well you can actually control the system. So for this particular system where we've got a MOSFET and it's a relatively quick to respond, I'm going to set the frequency at 5 kilohertz. It could be 1 kilohertz, it could be 10 kilohertz. It'll probably work just fine either way. And then I need to set the duty cycle, and because this is at the start of the code, the program, I'm going to set this to 0. So basically the MOSFET is going to be switched off, and when the MOSFET's off, the heater's going to be off as well. I'm going to make a really simple control loop now. It's not going to be a PID controller, it's just going to be an on-off or a bang-bang controller. So what I'm going to say is, if the temperature reaches 35 degrees or above, keep the heater off, and any temperatures below 35, keep the heater on at full power. So there's no proportional control here or anything. It's basically, if you're below the set point, heater's on. If you're above the set point, heater's off. So we need an if. If the temperature is greater than or equal to 35 degrees C, then I need to set my PWM duty to 0. Else PWM.duty is on its maximum setting, so it's on all the time, which is 65,000. And that's it. That's the simplest control loop one could ever get. So when I run this code now, nothing's really going to happen because I haven't turned my DC power supply on. So let's get my hand on the output. So watch this. What we should see is the temperature rise to 35, then oscillate around that value as the heat is switched on and switched off. Here we go. So you can see it's overshot 35 quite a lot. My heater's off now. I can see there's no current draw on my DC power supply. Now as soon as it hits 35, my heater comes back on full power, and that again causes it to overshoot past 35. And it's going to bounce around like this forever. You know, if the ambient air in my room was colder, then it would drop down to 35 quicker and this oscillation would be quicker. You get the idea. There's no kind of control here, just switching on and off as you reach 35 degrees. So that's the most basic form of control you can do. So let's modify this code now to actually implement a proportional controller, or the P part of the PID. We won't go for the full PID to begin with. So to do that, we need a few things. We need a proportional constant. I'm going to call it Kp is equal to, and this is the big question, what should it be equal to? So I'm going to do a really rough calculation here. I'm going to say temperature in my room is around 20 and my set point's 35. So the biggest error I'm going to get is around 15 degrees C. I know that if I set the duty cycle to my Pi as 65,000, it's going to be on full, and if it's 0, it's going to be off. So when I've got an error of around 15 degrees, I'd like to be telling the Pi that you should be on full power. You need a value of around 65,000. So I'm going to do a simple calculation. I'm going to take 65,000 and I'm going to divide it by my maximum error, and that gives me a value of around 4,333. So I'm going to set my Kp gain to around 4,000. So that means if the error is big, the duty cycle is going to be big. It's going to be almost 100%. And if the error is small, obviously the duty cycle will be small. Okay, so that's the Kp gain. This can be tuned. This is your job as an engineer to be able to change this value and find the right value for your system to get the response you're looking for. We're also going to tell the system what set point we actually want. So I'm going to say 35 degrees. So now let's look at our loop, and we still need to read the temperature obviously, and we're still going to print it out. But we need to do a few things. So first, let's calculate our error. So error is equal to the set point minus the measured value, the temperature. Okay. And then we're going to control, so we're going to make another variable called control, and that's going to be equal to our proportional constant value times our error. And that should be it really. We should be able to put control directly into PWM duty cycle and the system will work. We can remove this loop now. However, we need to be a little bit careful about this value. So the problem is twofold. Firstly, the temperature is not an integer number. So when you times that non-integer by 4000, you might get another non-integer. This duty cycle has to be an integer, so it has to be a whole number. So we have to fix that. Let's write some code to do that. I'm going to call it duty cycle. Duty cycle is equal to the integer of that control parameter. Okay, simple as that. So now if that's 30,000.2, it's just going to go to the duty cycle as 30,000. We also need to be a little bit careful that we don't put any negative numbers or values bigger than 65,000 into our duty cycle, or it'll cause our code to crash. So that's easy. We're going to put a couple of little lines of code. So if duty cycle is less than 0, in other words, it's a negative number, which is really easy to get because if you think about it, if your temperature goes higher than 35, you're going to end up with 35 minus, let's say, 36, and that's going to give you -1. That's a big problem. We can't enter a negative duty cycle. So if duty cycle is equal to 0, less than 0, then duty cycle equals 0. So now if we get that over the set point temperature, we're just going to turn the heater off. That's an easy one. I'm going to do an else if. And if we go bigger than 65,535, then we need to just set our duty cycle to the maximum. Can't go higher than that. We can take that out. Oh no, we just want to put duty cycle here. Okay, so that's our code. Let's run that code now. So the heater's off at the minute, so it's just going back down to the room temperature. And let's turn the heater on. So you can see the temperature rising up. And as we're approaching 35, you can see it's not increasing as quickly. But now something really interesting has happened, right? You can see that we've not ever made it to 35, and it looks like we're never ever going to make it to 35. And there's a reason for that, which I'll explain later. Let's just see the effect of changing that KP value now. So I'm going to stop this code running. I'm going to turn my DC power supply off. Now I'll stop the code running. And I'm going to change my KP gain. Let's make it 10 times smaller. And I just have to wait now. So I'm going to skip the video a little bit because I need to wait for this heater mat to cool down, or else it's just not going to work properly, is it?
A few moments later.
Okay, I've let the mat cool down a little bit now, so the DC power supply is off. Let's just start running this. I'm going to turn the DC power supply on now, and we should see a very, very slow rise. I can see the current on my DC power supply is like milliamps. This is because that duty cycle is absolutely tiny. There's barely any heating power, look. It's gradually creeping up. It's going to take hours to reach that set point value if it ever does. Okay, let's stop that. And we had 4,000 before. Let's set this to 10,000. Right, this is going to be a lot more dramatic. Let's run. So now you can see we've actually reached our set point. We've gone over our set point, but not bad. That's pretty good. And you can see it's oscillating around there, but again, it's actually beneath the set point value. We're not actually ever reaching 35. And this is where we need to add the I part of the PID controller. So in most of these systems, you actually get an offset error. So you want 35, but you get 33. There's an offset. You'll never overcome that. And that's because of losses in the system. So let's just think for a moment, what's going on? Why are we getting this offset? So imagine our measured temperature is 33 and our set point's 35, so there's an error of 2. An error of 2 times our proportional gain constant gives 20,000. Basically, let's just assume that's the duty cycle of around 33%. I'm not calculating it, it doesn't matter. But 33%, that keeps the heater on 33% of the time, but that might not be enough to reach that temperature. Okay, it knows nothing about the external environment. As I move my arm over, I'm basically actively cooling that heater, and we're just changing the duty cycle ever so slightly because the error is so small. What we need is something that actually recognizes there's this constant offset and overcomes that, and that's where the integral controller is so important. So let's look at how we might integrate an integral component into this system. So there you saw a proportional controller, and clearly there was an offset. We never actually reached our set point value, and that's because of losses in the system. So we saw an error, a steady state error of around a few degrees. So if you think about it, that few degrees times our proportional gain gives you a duty cycle, and that duty cycle is keeping that MOSFET switched on and that heater on. But there's no guarantee that that amount of heating power is sufficient to reach our set point. There's losses, there's all sorts of stuff going on. There's losses in the wires, there's drafts in this room that are cooling that heater down. This is causing this steady state error. So we need to introduce a new term, the integral term, or the integral component that gets rid of this steady state error. So let's have a look how it works. Looking back at our example of heating a room now, you can see here we've gone up and we've reached some kind of steady state away from our set point. So here we're at 20 degrees, slightly above, but let's just pretend it's 20. And that's generated an error. Every time we go through our measurement loop, we see that there's an error of 5 degrees C. So this integral term, what it actually does, it starts at 0, and then every time there's an error, it adds it to itself. So let's just imagine that the integral component here is 100. So it's added up all these errors up to this point and reached a value of 100. When it does this measurement now, it's going to say integral equals 100 plus 5. So this value becomes 105. The next time you run this measurement loop, you've got another error of 5. So this time you're going to say integral equals 105, add 5, so it becomes 110. And now on this one, you're going integral equals 110 plus 5 becomes 115. So that integral value grows even though the error stays steady. And that is the most important point. And it eliminates that steady state error because it increases your control signal every time your loop runs until you reach the actual set point value. And then it stops increasing, obviously. So let's go and have a look at that now. Let's implement that integral control and see if it eliminates our steady state error. So what I'm going to do now is, let's just put that back to around 4,000. I kind of like 4,000, sensible. We need a KI term. I'm going to set that to 100. This is a pure guess. Okay, that's our integral gain. So let's modify our code now to implement this integral term. So what I'm going to say is our integral is equal to integral plus error. Oh, something's happened. So let's think about what happens now. So every time this loop runs, the error is going to get added to this value called integral. So it starts off at 0. Let's imagine the first time this loop runs, we get a temperature difference of 2, so error 2, then integral becomes 2. The next time the loop runs, if the error is still 2, we're going to do 2 plus 2, integral becomes 4. If we run again and the error is still 2, we're going to do 4 plus 2, the integral is going to become 6. So this is accumulating the error. The longer that error remains, the bigger this integral value is going to become. Okay, so that's the integral value. Let's create our integral term now. Is equal to our constant ki multiplied by our integral. That's all we need to do. So now when we come to our control parameter, we're going to do, that's our proportional term. We're going to add our integral term. And that's all we need to do. Now we've actually got a PI controller, not a PID, not a P and an I controller. Let's run that. You can see temperature's 24.75, whatever in my room. Let's turn the heater on. See what happens now. So you can see the temperature's increasing. It's approaching 35. It's overshot quite significantly. That means our integral term is way too big, if you ask me. Wow, that's really, really awful, isn't it? Let's stop that running, turn the heater off, stop that running. Let's change this to be something like 2. $10. Let's see. I'm just going to let the heater cool down. Okay, let's run again. So we can see our temperature increasing. And there we are, we've not overshot now, but also we should actually creep towards 35, we're quite close. See, we're actually on 35 now, that's not bad at all. There's no offset, the integrals remove the offset, and that's the important point. And for a lot of systems, especially if you're doing things like heating water, this is all you need. You don't need to go any further than a PI controller. The differential's slightly different, and that actually reduces the heating power. So one thing I should mention, if you look at the PID diagram, obviously an integral, there's got like a time term, there's something to do with time there. And that's important, but basically it's because I'm only running this loop every second, my time term is 1. Basically I'm only, dt is 1. So I don't need to factor it in. But if you're running this loop as fast as you can, you need to factor in that dt. So to implement the dt term, you basically go to your integral term and you times dt. But basically in this scenario, dt equals 1. So the final term to implement on our PID controller is the D part, the differential component. And basically the differential component reacts to the rate of change, as you might tell from its name, differential, of the error. This actually provides a damping effect to reduce overshoot and improve stability. So let's have a look at how this works. So let's imagine I've just turned my system on, I've just flicked the switch and we've measured the temperature, and you can see here temperature is really low. It's around, I don't know, 5 degrees. So that's generated an error value of 20. At some time later, say 5 minutes later, we've measured the temperature again and we've found that the temperature in the room is 10 degrees. So now our error is only 15. Okay. We calculate the differential by doing the current error minus the previous error. So in this little example, current error is 15 and our previous error was 20. So we've got 15 minus 20 gives us this differential component of minus 5. Minus, right? So that's actually a negative number. So when we add this differential component to our control signal, we've basically got a positive number, and now a negative number. So this is acting to reduce the control value, and it's slowing down the heating process. And the quicker you change, the bigger this number is going to be negative, the more negative it'll be, and the more it will act to slow the heating down. This makes a lot of sense, because if you imagine between 2 time points, if you've made a massive step towards your set point, you've basically very likely that in the next measurement, if you continue at this same rate, you're going to be way above your set point. So this differential term sort of predicts that, and it acts to reduce the heating to stop that massive overshoot. And of course, this value actually becomes positive if you're above the set point as well. So here, KD, a set value of, I don't know, 100. So for KD, we need another term, another variable. We're going to call it previous error. I'm going to set that to 0 to begin with. So now we calculate our error, we calculate our integral term. Let's tidy this up. P equals that. I equals this. So we're going to do P plus I. Let's have our D term. So D is our, a differential term. And to do that, we need to do derivative equals error minus previous error. And then our derivative underscore term is equal to KD star the derivative to be consistent. Let's call that the D. And that's star our time. Okay, let's give that a try. So I'm going to stop that running. And I'm going to turn on my heater and the code. Let's watch what happens. Again, a little bit of overshoot. We probably need to increase that D term. So if I was tuning this sort of, for a professional job that I was being paid for example, I'd plot these graphs, I'd save these numbers, and I'd actually look at the responses, the full response, and I'd tweak them until I got the quickest response I could with the least amount of overshoot I could live with. So I hope that explains the PID controller for you. So just to summarize this video, PID controllers are not as complicated as this diagram makes them appear. But I mean, look at it. Now you understand how that PID controller works and its various elements. This diagram makes sense, right? So you have a process which there's an output of which you measure. You take that output and you compare it to your set point. So our set point was 25 degrees in our example, and we measured a temperature of 20. So we generated a value of 5 for our error. For the P component, we took that error and we times it by our constant, our Kp. For the integral term, we integrated all those previous errors and times it by our Ki term. And for the differential term, we took that error and we differentiated it and then multiplied it by our Kd term. Then we took those three P, I and D components, we summed them together, and we used that value to adjust our process. So in the example, that was the adjustment of the heating power to our heating element, be it the boiler or the little heating mat I have in front of me now. That changes the temperature and the process repeats. And that's a PID controller. You can use this for basically controlling most systems. All you need to do is tune the Kp, Ki and Kd appropriately, and you can always get that critically damped response. So I really hope you found that video useful, and thanks for watching. Of course, if you've got any questions, put them in the chat, and don't forget to subscribe. See you in the next one.